Hey, everybody. All right. So I am Dead Program. In the real world, some people call me Dad. Some people call me Ron. But I am Dead Program on the internets, Twitter, GitHub, all the places. And I'm a technologist for hire. I was told to be really subtle about marketing, so working on that.
I am Salvador Evans. I am son of Dead Program, or his apprentice.
Whoa. Powerful. And so we run a small consultancy called the Hybrid Group, where we specialize in writing software for hardware companies, where we are all technologists for hire. Okay, marketing people happy. So we've done work for many different clients building the software for their hardware. Very recently, we've been doing a lot of work for a really cool company called Northvolt, which is Europe's only lithium-ion battery manufacturer, company based in Sweden, doing all the batteries for the new BMWs, so very cool company. And we've done a lot of work for a little company you may have heard of called Intel. But we've also, along the way, created quite a few different open source projects, in particular in the Go programming language. GoBot is very well known among people who create middleware, sort of like the middle layer runs on embedded Linux. GoCV, which is computer vision in Go. It's a set of wrappers around OpenCV, which is a computer vision framework, very popular and commonly used. And today we're here to talk about TinyGo. So TinyGo, which is now officially sponsored by Google. Thank you, Google. We really appreciate. You can applaud. I applaud every day. So as many of you know, Go is big in the cloud. Right? Go is really big in the cloud, by which we mean Go is big. By which we mean that Go executable programs are very large. And Hello World in Go is in Go 1.13, which is the release right before the most recent release last week. Even we didn't know the date of that release, by the way, so don't ask us. So Go programs are very large. And luckily, though, that's not a problem because clouds are infinitely scalable. Right? You look up, all blue sky. But what about the small places? Right? What about the little places, by which we mean microcontrollers, which are the small chips that actually run all the things in the world you care about, like the dialysis machine or the brake systems or other types of mission critical, the refrigerator. And WebAssembly, which there was a really cool talk right before this from a true expert in WebAssembly. So what we're talking about is true edge computing. Not this, so-called edge computing. Edge computing is not the data center nearest you. I am sorry, I must respectfully disagree. The real edge computing is in what we call the last centimeter, right? So that's what TinyGo is here for. So how TinyGo works, just very, very briefly, is it's a trinity between Go, TinyGo, and LLVM. So the Go compiler itself is written in Go. Right? All cool languages eventually reach a point where they can be compiled in themselves. It's a very self-referential, but it also proves that it works. So the Go compiler toolchain is written in Go, and a lot of the things that it uses are actually built into Go standard library. Then you've got LLVM, which Justin talked about this morning, and I'm sure many other people have mentioned. It's a framework for building compilers. It's being used by a couple of languages you may have heard of. One of them is a very cool language called Rust. We really admire the Rust community.
Which he knows nothing about.
I know a little more than you think, kid. Also Swift, another very cool language. Some other cool languages recently, Zig, very cool language, written LLVM language. There's others. So TinyGo, the way that it works is we take the source code of Go and we pass it through the Go standard libraries to create the Go single static assignment form, which is taking the Go code and reducing it down to this very reduced type of syntax. Then we take that and TinyGo translates that into LLVM intermediate representation, which is what LLVM's toolchain takes, and then using tools like Clang or LLD, which are the built-in toolchain that LLVM itself provides, we can then compile targets in LVM for very, very small places. So let's start with the hello world of things, which is, of course, a blinking LED, right? So for this, we're going to use a DigiSpark. A DigiSpark is, you can hand me the DigiSpark now, please.
Pretty sure that's a Digimon.
A Digimon? It could be. So the DigiSpark is an AT Tiny 85. I just like the word tiny in it. But it's an 8-bit processor. Let's go to the camera here real quick so you can actually see it. So it's an 8-bit processor. It's really small. You can barely see it. That big thing on there is not the AT Tiny. That's the power regulator so we can plug it into your USB. That is the AT Tiny, that other little one next to it. Right? So the AT Tiny has only 8K of memory, and it's an 8-bit processor. So of all of our pleasures, we're going to start with the gentlest. So let's take a quick look at the code for the hello world of things. Who here does not know Go at all? Well, welcome. So, yeah, we're working on that. Working on that. So Go is very similar to languages that came before, so there's many things that you will recognize. In Go, we have the package main, which is the main executable unit. We can import external libraries, similar to require in JavaScript or Ruby. So we're going to import the machine package, which is part of how TinyGo knows how to talk to hardware. We're going to import the time package, which is one of the Go standard libraries for managing time. And then we'll declare our function main. Our function main, just like Python or C or other languages, that's our entry point into the program. So we're going to say LED : equals machine.led. : equals defines it and also assigns to it. So it says that this LED is of whatever type this is, machine.led, and assigns it. So then we're going to configure the LED so it's an output pin. When we're working with embedded devices, most pins are either output, making something happen, or input, reading something from the world. And then in Go, there is no while loop, there is only for. And if we say for with no parameters, it means forever. So forever, we're going to led.low, that sets it off, sets it to a low level in 5-volt TTL, low 0 in binary syntax. We're going to time sleep for 500 milliseconds, 1/2 of a second, do nothing. Then we're going to led.high, which turns on the LED, 1 in binary, and then time sleep for another 500 milliseconds. All right, so let's run this. And if the demo gods favor me, as they will sometimes do, oh yeah, DigiSpark. So I'm going to run this program. It compiles the TinyGo program, which you'll notice is 398 bytes in size. And it's asking me to plug in the device. So I'm going to plug in the DigiSpark into my USB port so we can flash it. And it erases it, and now it's flashed. So now, if I have a battery handy, which I do somewhere, here we go, and I plug it in.
We had 25 minutes to prepare for this.
Oh, here's a battery. This was another classic case of the battery is a lot larger than the device. And if I go to the camera, you will see that the LED is flashing and there's no wires attached. Nothing up my sleeves, folks. All right. So now let's see some basic input and output. So for this, we're going to use a DigiSpark again with an LED and a button. So same DigiSpark, same 8-bit processor. So this program is very similar, package main. We import the same machine and time packages. We have our LED that we declare. We also say button : equals machine.p0, which is the pin that the button is plugged into. We configure that as an input pin. That way we can get the input. Then forever. If button.get, which gets the value either true or false. If it's pushed, then we turn on. Otherwise, we turn off, and then we wait 10 milliseconds to see what happens then. So let's make button. That one is 206 bytes. Oh, how is it smaller? We keep getting smaller. Eventually, we're at negative bytes.
Again, 25 minutes to prepare.
All right. So we plug this into our battery again. We go over to our camera. And as I push the button, you see the LED turns on. Morse code. I'm sending a message to the past. It says, please stop using carbon and helium. I need that helium for my blimp. All right. TinyGo blink with button. So how does TinyGo actually know about hardware? I mean, that was neat. Like, you showed me 20 lines of code and it did something, but how does that actually work? Well, for that we have to go inside the chip. I mean, way inside. I mean, deeply inside. I mean, all the way inside to what are known as registers. So you may have heard of registers. Somebody said something about the assembly language registers, and you're like sort of tuned out in class because you were thinking about something else. I like to think about registers like little valves. Like, you turn them on and off, and then they make the electrical circuit work kind of like the water flowing through a series of pipes, series of tubes, like the internets themselves. So when we have a microcontroller, especially the ones that are created by all the different ARM licensees, they actually provide a description of all the different capabilities built in a file that's known as a system view description file, or an SVD file. So here's a tiny excerpt from one small part of one SVD file. You'll notice that it's in XML, one of our favorite markup languages. And this is describing the port. The port is how we are able to turn the blinky on and off or read the buttons, and it tells us which address the offset that is at, all this information at a very low level. So we take those SVD files and we use them to generate Go code. Like, we read them and we actually parse them and generate Go wrappers for them, something which is also done by Rust embedded, is also done by Python. Other languages do, we're just using the same techniques. So we create something called the device package. The device package takes that and it turns it into a Go type, where now we have like the direction, whether it should be cleared or set. But this itself is very, very low level as well. And it's very, very hard to work with these individual bits on individual registers, even if it's in a higher level language like Go. So here's an example of where we're setting the output port of that one bit, bit 3, to set. That's how we're actually turning the blinky LED on and off on that digispark. But that's a little too low level, right? So instead we have the machine package on top of the device package. The machine package is what our hardware abstraction layer is. So this is how the set implementation works. We look at the pin number. If it's less than 32 and you're turning it on, then we're able to set that pin on. Otherwise, we clear the pin, right? So it's still pretty low level, but at least it gives us the ability to say pin.set off or pin.set on, and it knows exactly which register and which bit within that register, and that's all taken care of for you. So we have wrappers around the typical peripheral input-output, general purpose input-output, or GPIO. So this is the code you saw before. LED machine.led, configure it as an output pin and set it to true, right? We also have support for UART, which is Universal Asynchronous Receive Transmit, SPI or SPI or SPI, depending on which generation you come from, which is Serial Peripheral Interface. I2C or I2C, again, depending on how much gray hair you carry, is the inter-chip communication. That's how all the chips on a single board can communicate with each other. And so let's see an example that puts this all together, and let's use our DigiSpark just one more time. So we're going to use the DigiSpark with a strip of NeoPixel LEDs. So these LEDs are actually each individual microcontrollers themselves that do nothing more than control the RGB LED, and each one of them is a separate microcontroller. And so we're plugged into our DigiSpark, and it's going to, at very high speed, send these signals to the LEDs. Now the way that this works is thanks to the TinyGo drivers. So the TinyGo drivers are our library of all of the different types of devices that we support: digital thermometers, accelerometers, different lighting controllers. I think we have about 40 different devices currently supported by the community, with more being added all the time. So we're not going to go over every single bit of code. but just to kind of give you an idea, same package main. We're going to import the Go standard image color package. That way we're just using normal Go code for color assignment. Machine and time, our friends from before. And then the WS2812, that's the real chip name for the Adafruit NeoPixels. But NeoPixel is a much cooler branding title, but you can use, random, LEDs that you've acquired for various sources as well. They will probably work. So we have an 10, because we have 10 different LEDs. Actually, I think I changed this, but we're not executing what's in the slide, luckily. So we've got our LED, we've got our NeoPixels on pin 0. We say WS2812.new in Go. This is how we sometimes will have a constructor. Right? It's going to return one of these, and it's going to assign it to that pin, pin 0. And then forever, we're going to go through and set these LEDs to each one on and off. For this one, it's going to be red and green, so kind of Christmassy theme. We're going to write those colors, and then we're going to sleep for 100 milliseconds. So let's go to the demo. So if we make NeoPixels, this is a whole 728 bytes. Well, but before I flash it, one really key thing to know is the only way to get this kind of high-speed performance, thank you. The only way to get this kind of high-speed performance is you need to use assembly language. You need to use assembly language in any programming language you program these NeoPixel lights in, because nothing else is fast enough to send the updates, especially if you end up with hundreds of them in a string. We'll see some of that later. So one of the things about TinyGo is we can actually compile assembly language code right into your TinyGo code. So in this case, we're using AVR assembly language. And this is just a small excerpt of it. This is how it's able to combine the Go code. The Go code figures out which is the pins to set. And then the assembly language actually does the setting. Okay? So let's compile that program. Oh, there it was. Let's plug in the NeoPixel through the DigiSpark. All right, so now, if you don't mind plugging this in, while I go to the camera. And if you've plugged it in the right direction, it works.
It's meant to not work, we swear. It's a comedy. I can...
Oh, thank you. Yes. All right. So this comes time for our ever-popular Choose Your Own Hardware adventure. Thanks to our lovely sponsors, we have some hardware to give away for you to be able to learn and experiment with TinyGo. So you can win this cool hardware, and all you have to do is go on to the Twitterverse and tweet something using the hashtags TinyGo and QConLondon. Okay? You can win either a DigiSpark, which I will solder it together for you in my hotel room if you need be, or an Adafruit Itsy Bitsy M4. An Itsy Bitsy M4 is...
Is that the right thing?
No, but it's OK. Anyway, it's the chip that we are actually going to be using for some of our next demos. So all you have to do is tweet something nice, like best demo I've ever seen, most handsome presenters, and his dad was OK too. All you have to do is tweet this, and we will be giving it away not right after the talk, but at the reception right after the talks are concluded. That way nobody's distracted with the next speaker, which I want to see myself, actually. So now back to the show. Bouncing ball using the Pi portal. Can I have the Pi portal?
Yeah,
That's
sure.
the Pi portal. So the Pi portal is an Arduino, no, it's not an Arduino, it's Adafruit. Copy and paste error. It uses the microchip ATSAM D51, which is a 32-bit ARM Cortex M4 at 120 megahertz using 256K of RAM. That's pretty large, lots of headroom for us in TinyGo land. It also has a built-in Wi-Fi chip, the U-Blox Nina W102. It's basically the same as the ESP32, which is the Express-IF Wi-Fi chip that is really commonly used in a lot of different devices. It runs at 240 megahertz. You need to run a lot faster processing speed just to do SSL, basically, so that's the reason for that. Don't have time to show you all the code, but you can find it here on the TinyGo drivers website. We link to it. And so let's take a little look at our demo here. You can hold it under the camera, please. So this is the Pi portal. We can peel the plastic off. Flip it over, please. You can see it's got the Wi-Fi chip. It's got room for an SD card. It's got a few different sensor buttons and connectors that we can plug in. So this demo is actually a really cool one. Make ball. We plug it in, if you please. So this is a bouncing ball demo, and so let's flash it. We have different flashing software that is currently supported by TinyGo. This is a whole 27K program that's like really large. And what it does is it shows us a bouncing ball on the screen. There we go.
Does it just bounce?
Yeah, that's it. So, really cool demo, right? No, it sucks. Here's why. As cool as this is, we're not even using a fraction of the processing power in this 32-bit microcontroller. I know, you're like, wait, it's bouncing around, it's like physics, and like, no, we can go so much further than this, right? Let's take a look. It's time for the LED cube.
Oh,
so, yes. So unplug that, please. Thank you. So the LED cube is, I like to call it the cube of fire. So it's an itsy-bitsy M4 with 6 little tiny, in relative terms, LED displays using a board called the Hub 75. So the Hub 75 is what's used on these giant stadium-sized lighting controllers. They just have many, many of them all stacked together. So we're going to use 6 of them to make this cube. And it uses the itsy-bitsy M4, which, as I mentioned, is a ARM Cortex M4, 32-bit processor. This has 192K of RAM, so even tinier. And the Hub 75 LED panels. So in order to achieve this, we're going to need to use direct memory access. Direct memory access is a way that we can do very fast input-output, I/O, by letting the actual I/O devices talk directly to the memory, leaving your microcontroller free to do other things. And we're going to use interrupts. So interrupts in embedded software, and any software really, are when something happens that has to be handled right now, it can send a signal to the main processor called an interrupt. That interrupt tells you, stop what you're doing right this second and do this other thing. You know, shut down the battery before the meltdown, or in our case, we want to be able to update the display while we're rendering what's happening on the next. So to do this, we have, here's an example using the UART, where we set our interrupt. We declare a new interrupt in Go, again, saying when this interrupt occurs, call the handle interrupt function. We set its priority to C0, so not super high priority, and we enable it. So the function in Go that we call when that interrupt is triggered says, get from the register the value that's just been typed by the user on their keyboard that's connected to the UART, and then let the rest of the code know about it. So if you want to see the code for the cube of fire, the code is currently on my collaborator IK's personal.
You do realize it makes absolutely no sense for it to be called a cube of fire unless you do the thing.
He says it makes no sense to be called the cube of fire because we don't have any fire. Good point. Let's fix that right now.
I swear to God, this was not scripted.
All right, so let's take a quick look. So if we go over to, let me make sure I actually switched to the right code, because I'm known for doing these things at the last minute. Plus, this way you know it's real.
Of course.
He went in and changed the code. So yeah, the noise demo is what we're seeing right now. Let's use the fire demo. All right, so if we make cube, and it's plugged in, it also wouldn't be on. So it compiles 21K of code, and the cube of fire.
Now it's actually cool looking.
So you don't see anything on top because, fire goes up. from the bottom to the top. So we have a whole physics simulation of fire running on this 32-bit ARM microcontroller, doing all of this stuff at a pretty decent frame rate.
Should I just tilt it?
Yeah, that looks pretty good. Oh yeah, that looks great. So as promised, the cube of fire. Very special thank you to Adafruit for sending me these panels, because our normal Chinese suppliers have been kind of busy lately. And you know, I just want to say how much we appreciate all the efforts of people in China to try to keep all of us healthy and taking a sacrifice for planet human. Thank you. All right, so.
It's a cube of fire if you have the imagination of a 6-year-old.
Yeah, what's fiery enough? All right, let's move on, shall we?
Yeah,
All right, so a bunch of you have seen us wearing these badges around today.
Oh, yes.
So these badges are also written using TinyGo. So any of you who know me or have seen my talks know I like to fly things. So don't plug it in the bed yet. So I also like programmable badges. So I thought, you know, the only thing better than a programmable badge is one that we use to fly a drone.
Of course.
Just because that's how
Everything
we do
is
it.
better with drones.
Everything is better with drones.
Objectively.
That I totally agree. So I may have mixed this up. I guess we'll find out when I take off, right?
No, that one's yours.
Yep, this one's mine. Okay, very good. So we're going to plug in this joystick into the ports on the badge, conveniently provided. So this is a Go badge. A Go badge is actually a Pi badge from Adafruit with a Go Bridge sticker on it for now, but we'll fix that. So I'm going to plug in the badge, and then we'll take a quick look at some code here. If I can get it plugged in correctly, there we go. All right. So it's using the Pi badge, as I mentioned, which is another ARM Cortex M4, 32-bit, running at 120 megahertz. That's kind of like the chip du jour. And we're going to communicate using the USB Communications Device Class, or CDC. This is how we can make a device use USB and act like a serial port. So this is the architecture of it. We have the Pi badge. It reads in the buttons using the GPIO interface, reads the joystick using the analog I/O. Then it's going to send updates to the little TFT display that's built in and send the information about the drone control to the USB. We don't have time for all the code, but just a brief look. We have our devices from the TinyGo drivers, the display and the buttons. We have our SPI interface, which is how we communicate with the display. You'll notice here that we have a Go routine, Go handle display. Yes, TinyGo is just Go. We don't consider ourselves separate from Go. So we have the concurrency capabilities of Go. So when we say Go handle display, it runs this function as a Go routine and then immediately returns while that function is still executing by itself. So we're going to initialize the analog to digital converter. We read the joystick and the buttons, and then based on that, we're just going to send that information out the serial port. This is the function that's running in the Go routine, which is displaying on that little display the buttons that we push and the readings from the joystick. All right, so let's flash it. What's it called again? Flight badge, there we go. So let's flash it. 19K program. And it's a little hard to see with the camera, but you can see that.
It's there, we swear.
Yeah, okay, good, I got it correct. The X and the Y axis. When I push the buttons over here, that's going to be takeoff.
Wait. If it cuts your head off, you can't sue us. I swear it's somewhere in the contract.
Oh, don't forget to put the battery in.
The battery?
Push the battery in.
Oh, very good.
All right, so we see the Go badge, the flight badge, as it were. All right, so full application is actual flight control. So for this, we're going to have our flight stick that we just programmed, a ground control system running on my notebook that actually uses computer vision to do deep neural network recognition of people's faces, a Tello drone, which is that drone. Can you bring the drone back over here real quick, please? And an MQTT server, which is Mosquito, which is an open source machine-to-machine messaging broker currently maintained by the Eclipse Foundation.
It's not child labor if you don't pay them.
That's a fact. That's what my mom told me. So this is the Tello. The Tello is a very cool, are you sure you plugged it in? Oh, didn't turn it on. So the Tello is a very cool drone. Oh, there we go. It's made by DJI, the Chinese drone company. It actually uses in it a special chip called the Movidius X. The Movidius X is a chip made by a company that Intel bought called Movidius that is a specialized chip intended to do deep neural networks and other types of concurrent computing. So it just so happens that that is also controlling the flight system in this drone. Can you take the drone back to the takeoff point, please? And point it towards them, not towards me. Not like last time. All right. So we're going to bring in GoBot. GoBot is what's running on my notebook computer. That's kind of our middleware. The DJI drone, we talked about that it's a Movidius 2. We're also going to use GoCV to do the computer vision part. Here is a quick look at the architecture. We're going to use the Pi badge as our flight stick. The ground control system is going to read that information and use it to send commands both to the drone and to our machine-to-machine messaging broker. And then using the UDP packets of the video, we're going to send that through our computer vision. I'm not going to look at all the code, but the two parts that are most interesting is when we set up the drone that we're actually going to grab that video, and that as we get the flight data events, we're going to post those to our MQTT machine-to-machine messaging server. Okay? So far, so good. So let's see if we have everything plugged in. Yes. And let's see if I'm connected to it. No. Are you sure the drone is on? Oh, wait, I didn't plug it in all the way. My bad.
Yeah, it was.
And it should connect to it. Yep, it did. Okay, excellent. All right, so I have a bad key on my notebook. All right.
At least you have a notebook.
That's true. At least I do. So let's go and before we do anything, let's go to our machine-to-machine messaging server, Mosquito, and we're going to subscribe to these messages that will theoretically be coming from the drone. And then we're going to go back to run our demo. And we make tiny drone. Oh, I should be holding the joystick at the time, probably, when it takes off, don't you think? Not a bad idea. All right, so it's connected. We'll know it's working because we should see a little video window pop up. Hopefully. There it is. It's looking at people's feet right now, searching for humans. We'll give it what it wants in a minute. It only has about maybe 10-minute battery life, so you just have to run faster than your friend for about 7 minutes. All right, and let's jump over real quick just so we can see the MQTT messages. Okay, very good. This other camera view. Yes. I don't need this camera anymore. Well, actually, we'll just leave it. Maybe it doesn't like them on top of each other. I'm not seeing any video updates coming. Makes me wonder if it's getting updated. Oh, well,
All this is scripted, we swear.
Let's shut down the other video.
It's supposed to not work.
Well, that builds, the intensity of the... Oh, yeah. Something went wrong.
Again, it's supposed to go wrong.
Don't tell them that. It takes all the drama out of it. Whoops.
But does it really?
I don't know. That's a worthwhile question.
Does it?
Don't answer that.
You should.
Nothing yet. It was running until I changed that window. Oh, yes. Oh, maybe the drone fell asleep because I talked too long. He keeps telling me that. No, it's still awake. It might be the conference Wi-Fi. No,
Or it's
I know it's
just
looking
your
for something.
incompetence.
It's definitely looking for something. Well, we can disconnect from the conference Wi-Fi.
So how was your Tuesday?
Thanks a lot. Way to believe in your dad.
You've shown me you're not to be trusted on several occasions.
That may be true.
Several may be an understatement.
Okay, well, we got to boot the drone up again.
Yay.
It got lonely and sad. Turn the power on. Let's take a look here. It should only take it a minute.
What's for dinner?
Tonight? It depends if they let you in the speaker dinner or not.
You do realize the only reason that people are here is because
Of you?
if it wasn't for me, they would all be watching the Tesla talk.
That might be true.
No, not might. It is.
Fair enough. I would be seeing that talk as well. Very cool company, doing very interesting things. All right.
So would I, but I'm your son, so.
All right. This time we're ready. Let's just go directly to takeoff.
Can I fly it?
No. Oh, there's a human now.
Again, you cannot sue us. Sue whoever organized it, please.
No, it's amazing. I've been told repeatedly, do not fly over crowds. In fact, I told my insurance person I did that, and first they started laughing, and they said, are you serious? And then they stopped laughing. And they told me never to do that again. And I only did a few more times before I stopped.
Can I fly it?
Can you fly it? No. Maybe another time. So one really important thing about drones is that you need to be able to do a flip. A flip is to the drone like a lens flare is to a photographer. It's overused, and I'm okay with it.
Can I do it the other way?
No, but I guess it's time to bring it in for a landing. Oh, wait, there's one really important thing we forgot.
Dad, it's gonna hit the roof!
Oh, shoot. It's okay now.
You want me to grab it?
No, I'll lower it.
I can control it.
Can you? Are you sure?
Yeah, probably.
It keeps coming this way. It's looking for you, Salva. It wants you to fly it. It wants to fly with you.
Come by.
It looks really neat with the shadow on the screen, though. Too bad the video people won't be able to see that. But all right, I guess, actually, the thing I did want to do real fast is show you that it actually is getting its MQTT messages. And we're at 65% battery, and there's no humans in the picture. Oh, yes, there are. See, it's got humans true and false at the bottom. Well, it's detected a few of you. I guess we should bring it in for a landing now before we actually do some damage. All right, there we have it. Cool. That actually wasn't too bad under the circumstance. So let's briefly talk about modern compilation targets, since in theory that's why you all came. No, but in actuality, the future of edge computing has already begun. There's a lot of people been working on it for quite a while. You know, we are just the latest to pick up the cube of fire and carry it along in our own little ways. So the future's future, if this wasn't future enough for you yet, the future's future is about RISC-V and is about WebAssembly. Well, the only way to make it better is if we combine both of those into a single demo, right? The demo that brings all the demos together. So we have something called the TinyGo Playground. The TinyGo Playground, there we go. Oh, did I disconnect from the Wi-Fi before? Oh yeah, I did. That'll make it really hard for that. So the TinyGo Playground is at play.tinygo.org, which I tell you in the slide, assuming that connection is established. Play.tinygo.org, so similar to the Go Playground, it lets you compile Go code in the cloud. The TinyGo Playground lets you compile TinyGo.
Yep.
Assuming that we can get to it. I know, you told me not to take chances. I should have listened to you. Why didn't I listen to him? He's going to remind me of that, like, for a while.
Because you deserve it.
Maybe. Hard to argue with that. Maybe we disconnect from this.
They came to see a talk.
There we go. Okay, the TinyGo Playground. So the TinyGo Playground, if we switch over to the board, the Sci-5, please.
Pretty sure they came to see a talk, not some middle-aged man fumble through his notes.
Is not true. They came to see disaster. Or success.
Success.
So this is a Sci-5 Hi-5 1B board. So that is a board that is made by a company called Sci-5 based in California and China. It uses a Freedom E310 processor, which is a RISC-V processor. It runs at 320 megahertz and has 4 megabytes of flash. So for this demo, I'm going to program it with a relatively straightforward kind of blinky program. And it's plugged in? Yes. So you'll notice that it's got a little simulator where it's blinking the LED. Right? This code is running entirely in WebAssembly. So what's happening is the Go program here, our play.tinygo.org, uses the TinyGo compiler running in the cloud to compile the RISC-V code to WebAssembly and then executes it in the browser. That way we can create a simulator which is not a simulator at all, which is actually the same code that we're going to run on the device. Don't believe me? Let's download by clicking this flash button. And we're not getting great network performance.
Lucky for
here.
you, there's only 8 minutes left.
Oh, we have plenty of time. Plenty of time. Assuming that it downloaded the file. There's one. So if I take this firmware file and I drag it onto the Hi-5 board, it will flash that board and then reboot it. And you'll notice that it's cycling through the LEDs. I showed you the code before. It's going red, green, blue. So we've actually just written a TinyGo program, compiled it using play.tinygo.org in the cloud, downloaded that hex file from the internet, and flashed it right onto this board right here, right now. The future is already here. Even the future's future is here. It's amazing. So tinygo.org. That's our website. You'll find lots of information. TinyGo itself is licensed under the BSD2 license, just like Go itself. So you can use it for commercial purposes or anything else.
Can I unplug this now?
You can now unplug it. All right. So, questions? Yes?
So how's the sort of real-time aspect of this? So, I mean, Go wasn't written to be real-time, but a lot of the stuff that you do, you need sort of real. I mean, talk to the LED strip and all that. If sort of garbage collection happens during a LED strip update, it'll fail. How's that working out for you?
It's working out really well. So the question is, how do you do normal Go type things like garbage collection and concurrency? So the answer is, we have our own runtime that we have written. So it's the Go programming language, but with a different runtime, because if you think about the way a Go program normally executes, it's running on some type of operating system. Linux, Mac OS, Windows, FreeBSD. And that operating system provides some lower level capabilities for talking to the physical devices in Linux. You know, they might be device drivers. So with TinyGo, we're using, as I showed you in the beginning, we're using LLVM. So we're compiling our TinyGo code to this very compact code. And because we've written our own runtime, we actually have multiple garbage collection implementations written, not all at the same time. You can choose which garbage collector you would like to use depending on your particular use case. You might choose to use what we call the conservative garbage collector, which basically, when it runs out of memory, will do garbage collection. We have that extreme to the opposite extreme, which is no garbage collection, which means when you try to compile your code, it will panic. It's totally possible to write Go code without using make, without allocating new memory, and you just basically using static memory assignment. So that might be a case where you want to use it. The second half of the question was, what about real-time capabilities that are needed for your basic types of embedded systems? Again, when we go to using LLVM, our first implementation of Go routines used LLVM coroutines. LLVM coroutines are a concurrency primitive based in LLVM. The problem with the LLVM coroutines is they have no knowledge of when they're executing. So they just pause anywhere inside the implementation of the coroutine in order to let other coroutines have a chance to execute. That's not very efficient. And it also doesn't let you handle situations like if you want to turn on or off the LED strip at the same time. So we then implemented our own task scheduler. So that way we have more control over the times when this garbage collection occurs. So as you saw with the LED cube, we can get some fairly substantial performance. The LED cube does not use assembly language. This LED cube uses the DMA and the IRQs. The DigiSpark uses assembly language because there's no other way to do that on a minimalist microcontroller. In fact, if you look at the implementations in Python and JavaScript, every language, even Arduino's implementation, which is Arduino C++, they still use assembly language embedded in to talk to these particular kind of LEDs.
I've got a question. So what's the secret of the code being so small? Because obviously that's a big problem with Go. I mean, where are you saving the space?
So Go programs, the question is, how are you saving space? When Go programs themselves are so large, it goes back to the fact that we have implemented our own runtime. We have to implement a runtime that expects no operating system at all. And when you get rid of most of the runtime of Go, a Go program itself, it's actually quite small. This is a key benefit if you're writing Go for servers, because server deployment is quite simple. It's statically linked, so a single executable contains everything you need, right? Great for cloud deployments. We have the exact same thing for embedded device deployments, the difference being that we don't bring along the entire runtime, only the things that we actually need. Does that answer the question? Any other questions?
For financial support, please consider donating to www.givemydadmoney so that he can buy me a laptop.com. Again, that is www.can'ihaveyourmoneyplease.com or whatever I said the first time. And the sole purpose for me grabbing the mic is...
We thank you.
We have a budget.